Okay, so this is properties of water. Water is really odd. It has some really strange properties, and these are all caused by the fact that it can hydrogen bond really, really well. If you're not sure about hydrogen bonds, I suggest you go back and look at my video of intermolecular forces, which explains them, because you won't be able to really understand this unless you understand how a hydrogen bond works. If you're good at hydrogen bonds, then listen. There's three anomalous properties of water which you need to know about. They're the surface tension, the boiling point and melting point, and the density of ice, solid water, compared to liquid water. Okay, so we're going to start off with surface tension. And again, all you need to be thinking about for all of these is the fact it can hydrogen bond. All of these odd properties are because of that. So we'll start with the surface tension. Usually, if I have a tray and I fill it with a liquid, I'm going to have a surface layer of atoms on this liquid. Obviously, there'll be layers of atoms underneath. I'm not going to bother drawing them. I'm just drawing the top layer. Now, usually in a liquid, the only thing holding this layer of atoms together are weak intermolecular forces. So you'll have your van der Waals forces, your induced dipole-dipole forces, or if it's a polar molecule, you might have a permanent dipole-dipole force. These are both incredibly weak compared to hydrogen bonds. So if my little gecko lizard was to stand on this layer of atoms, because there's only weak forces holding these layer of atoms together, the gecko lizard will push through them, break the forces, and sink to the bottom. And die. However, with water, because water can hydrogen bond, it's got these strong forces holding them together. These hydrogen bonds are incredibly strong. They take a lot of energy to break them. So if you have a molecule, if you have an animal or an insect light enough, like an incredibly small lizard or pond skaters or insects like that, they can actually stand on this, and it's like standing on like a layer of atoms holding it up. They can't break through this top layer because the hydrogen bonds are holding it together because they're really, really powerful intermolecular forces. So the lizard or the pond skater will be able to stand on the water. So that's surface tension. Water's got a high surface tension because the hydrogen bonds in the top layer are strong and take a lot of energy to be broken. Okay? It's also got an incredibly high melting point and boiling point for exactly the same reason. Usually, in simple covalent compounds, the only thing holding them together are either incredibly weak van der Waals forces or fairly weak permanent dipole-dipole forces. Now, the boiling point of something, if I have my liquid, the boiling point is the temperature which that liquid changes into a gas. In order to change a liquid into a gas, all you need to do is break the forces between the molecules. Now, as I've just said, in pretty much all simple covalent molecules, the only forces between these molecules are incredibly weak, van der Waals or permanent dipole-dipole forces. So it doesn't take much energy to break them. Because it doesn't take much energy to break them, we only need a very low temperature to change it into a gas. Hence, the boiling point and melting point are very low. However, in water or anything else which can hydrogen bond, we've got these additional hydrogen bonds holding the molecules together. And these are really strong. So because these are really strong, these are going to require a lot more energy to break them. Hence, because they require a lot more energy, the boiling point and the melting point is higher. We're going to need a higher temperature, more energy to break these and change them into a gas. Okay? So that's why boiling point and melting point is higher in things which can hydrogen bond, like water. Okay, now density. Have you ever noticed if I have an iceberg, the iceberg will float in water? Now this is a bit weird. Usually if I have a solid, it will sink. Yeah, if I have liquid lead and a solid lump of lead, the solid lump would sink to the bottom because it's denser, its atoms are closer together, and the densest thing always sinks to the bottom. Ice is a bit weird in that solid ice, water's a bit weird, in that ice, solid water is less dense than liquid water. And the reason for that is, again, to do with hydrogen bonds. Usually, if I have a solid, and if I have a liquid, the solid is more compact, more dense than the liquid, so the solid will sink in the liquid. This isn't what happens with water. With water, it's the opposite way round. The solid is less dense than the liquid. So my liquid water is still going to be the same, and I'm going to have a few hydrogen bonds here holding the molecules together. But when we have a solid water, the molecules are held apart from each other. They're forced apart, and the thing which forces them apart is these hydrogen bonds. Hydrogen bonds have got a fixed length. They can't get shorter. You can't shorten a hydrogen bond. So when two atoms, two water molecules, hydrogen bond with each other, the hydrogen bond forces them apart. So in a solid, in solid ice, pretty much every molecule is hydrogen bonded. So every molecule is held apart at its fixed distance, so it's forced into a very low density shape. However, when we start to heat it up and melt the ice into water, we break some of those hydrogen bonds. So we've only got a few hydrogen bonds here. Not every water molecule is hydrogen bonded. So what the water can do, which isn't hydrogen bonding, is get closer. So our molecules get closer and closer and closer until we have a liquid where they're a lot closer to each other. So to sum up, ice is less dense than water because the hydrogen bonds hold the water molecules a fixed distance apart. As they get closer, they get closer together.